Hello everybody, this will be class number 1 for Pure Maths Unit 2 based on complex numbers. So complex numbers is a really cool field of math that seems to originate once we start taking a look at a small gap in math that we are used to, called quadratics. So if I was to give you the quadratic x squared minus 4x plus 5, how would we determine whether or not it has roots? Well, we would use its discriminant, which is b squared minus 4ac, which in this case, minus 4 squared minus 4 by 5 ends up being minus 4. So we would say that because it's less than 0, there are no real roots. Why is that the case? Well, if we take a closer look at the quadratic formula, we see that underneath the square root sign lies b squared minus 4ac. And because of that, this whole equation falls apart once you have a negative number under here. Because the number system we are used to dealing with does not allow a negative number to have a square root, or does not produce a negative number once you square something. But what if we could? What if there was a number that was the root of a negative number, say the most basic quantity? What if there was a number that was the root of minus 1? That would allow for this. That is where imaginary numbers comes into play. What we say is that there are no real roots, so there must be imaginary roots. So the symbol representing the root of minus 1 now is I, and this will be the most basic quantity that we're using. And we see that once you square I, because it's the root of minus 1, you get a negative number. So what happens when you raise this number to other powers? Well, there's an interesting pattern that arises. Firstly, when you square it, you get minus 1. When you cube it, well, that's just I squared by I, which is minus 1 by I, which is minus I. That can't be simplified any further. I to the 4 is I squared by I squared, but I squared is minus 1. So I to the 4 is 1. And if we look at the next set of numbers, I to the 5 is I to the 4 by I to the 1, which is I, and the pattern continues. It seems like we're going from I to minus 1 to I to 1, I minus 1, I, and then I to the 8, which is I to the 4 all squared, again, is 1. So what's really going on here? Well, it appears that the numbers that we're used to dealing with, if we use I as the most basic quantity possible instead of 1, it reveals a whole new set of numbers. The numbers that we are used to are just multiples of I to the 4 and I squared, whereas I cubed and I have been left alone in the dark for all this time. All the numbers, the entire number system that we are used to, is based on multiples of this. It's like half of it was missing, and by saying that I is the most basic quantity possible instead of 1, we bring out a whole new playing field of numbers. And it is when we combine the real and imaginary number system that we get complex numbers. A complex number is defined as a combination of real and imaginary numbers. For example, 1 plus I, 2 plus I, 4 minus 3i. Any possible combination of these two numbers will give you a complex number. If there is only this component, we call it purely real, and if there's only the I component, we would call it purely imaginary. And in complex number maths, the symbol that's most used to represent them is Z. So let's see what happens by using this new number system. What can we do to solve this equation now? So let's pull out the old quadratic formula, which says that x now would be equal to minus b over 2a, which is 4 over 2, plus or minus the root of b squared minus 4ac, so that's 16 minus 4 by 5, which is 20, all divided by 2a, which leaves us with 4 over 2 plus or minus the root of minus 4 over 2. Usually, we'd say this is where we stop, the whole thing falls apart. But because we have I now, we can do something interesting. If we split this into its components by using a law of surds, the root of minus 4 is actually equal to the root of 4 by the root of minus 1. But what is the root of minus 1? Well, we defined that as I, remember? So if we simplify things, 4 over 2 is 2. Root of 4 is 2, divided by 2 is 1. So the final answer that we get is 2 plus or minus I as the root of this equation. And if we want to check that over, we can substitute that root back into the original equation. So we have 2 plus I squared minus 4 by 2 plus I plus 5. Expanding this and expanding this, we get minus 8 minus 4i plus 5 now. Then 2 by 2 is 4. 2 by I plus 2 by I, well that's 4i here. Then we have plus I squared, but I squared, remember, is minus 1. Minus 8 minus 4i plus 5. Something interesting happens at this step, because you'll notice that the 2i plus the 2i minus the 4i all cancel out. The imaginary parts cancel out to leave us with 0, because 4 minus 1 is 3, minus 8 is minus 5, plus 5 is 0. So, by introducing I, we now have a root to this equation, which we did not otherwise have. Okay, so we've used that to find out the root of a quadratic. Let's play around a little bit. What if we have to find the square root of a complex number? Well, we should be able to figure out that the square root of a complex number has to be complex. Why? Because whenever you square a number in the real number system, you never ended up with a complex number. So let's suppose we have the complex number 3 plus 4i. We can write an equation which says that the root of 3 plus 4i is a complex number, and we'll let that be a plus bi. We can find out what a and b are. You should note that a and b have to be elements of the real number system for this to work, because this is a complex number, but a and b by themselves have to be a real number for this to be a complex number. If we square both sides, you get rid of this square root, and this becomes a squared plus 2 by a by bi plus this squared, which is I squared b squared. We can simplify this side to be a squared minus b squared, because remember I squared is minus 1. Now, in complex numbers, whenever you have an equation like this, because the two numbers operate in different number systems, whatever is complex on this side is equal to whatever is complex on this side, and whatever is real on this side is equal to what is real on this side. So we can actually extract two equations from this original equation. We can say that 3 has to be equal to a squared minus b squared, and 4i has to be able to be equal to 2abi. When we do that, we can simplify this one to be 2ab equals 4, which gives us ab equals 2, and b is equal to 2 over a. Now we can substitute this back into this equation to solve for a. When we do that, we have a squared minus 4 over a squared, because remember b is 2 over a, so b squared is 4 over a squared, equals 3. Now, we don't like this down here, so we can multiply this entire equation by a squared, which would mean that we now have a fourth minus 4 equals 3a squared. Bringing everything over to one side, we have a to the 4 minus 3a squared minus 4 equals 0. We can treat this as a quadratic, as if a to the 4 is x squared and a squared is x, and we can simplify it to be a to the 4 minus 4a squared plus a squared minus 4 equals 0. We can factorize the a squared out of this to give you a squared minus 4 by a squared, and then you can just pull 1 out of this to get you plus 1 by a squared minus 4 equals 0. Now, there are two possible options here. Either a squared plus 1 is 0, or a squared minus 4 is 0. But because of this, a and b being real numbers, we know that a squared plus 1 can never be 0. Because even though we have the imaginary number system at hand now, a was defined to be a real number initially. So this option of a squared plus 1 being equal to 0 cancels out. Not allowed to use it. The only other option is a squared minus 4 equals 0, which means that a is equal to plus or minus 2, and because we defined b as 2 divided by a, we know that b is plus or minus 1. So the square roots of 3 plus 4i, therefore, are 2 plus I and minus 2 minus I. Similar to the real number system, whenever you have the square root of a complex number, the different square roots will be plus and negative. So far, there's just one problem that we have with these complex numbers. How do we represent them graphically? And also, what sort of xy plane would we use to represent functions of complex numbers? In front of me, I have the real number line that we're used to. Every number here we've seen before, we know of, it's normal to us. Well, if we add another dimension to it, just like in a regular xy diagram, we have what is known as the complex plane. So what happens is the y-axis becomes the imaginary component, and the x-axis is the real component. So let's suppose we want to represent a number on this plane. Let's just pick this number here, the red dot. Now that we have it on a plane, there are different ways that we can represent it. Its coordinates would be 4 plus 4i. That's how we would write it. 4 plus 4i. That is this complex number here, based on its position. The x is real, the y is imaginary. Just remember that. Well, because it's on a plane now, there's another way to represent it. What if we thought about this complex number not just in terms of its x and y coordinates, but what if we thought about the angle that you had to go to reach that complex number on this plane? And what if we thought about the distance of this complex number from the origin? What could we do with a definition like that? So let's look at the complex number through that framework. We're going to look at it in terms of its angle, starting from this axis, going up, and the distance, which we call magnitude, from the origin. This distance here will be r. The angle in complex numbers is called the argument. Now we need to set some standards for the argument, otherwise things will start to get a little bit confusing. So the argument, firstly, will be in between pi and minus pi radians. We don't use degrees, we use radians in complex numbers. And also it must be taken from the positive x-axis. How do we get a negative angle? Well, any complex number that lies in this portion of the complex plane will have a negative angle because you need to go this way to reach it. And any number on top will have a positive angle because you need to go this way. So anti-clockwise is positive, clockwise is negative angle. And it's always taken from the positive real or x-axis. So just so we're familiar with the arguments, if a number lies on this line, well, of course, it would be purely imaginary, but it would have an argument of pi over 2, because this is 90 degrees, and 90 degrees is pi over 2 radians. If it was here, it would have an argument of pi radians, because this whole thing is 180 degrees. If it was down here, it would have negative pi on 2 radians as its argument, and here it would still be pi radians, because remember, it has to be greater than minus pi. So if you had a number that lies on this line, its argument would be pi radians, because it can't be both pi and minus pi. The standard was set that it would be greater than minus pi, and it could be equal to pi. So now let's take a closer look at this triangle here. So we're going to use some trigonometry to try and define the complex number by its angle and its magnitude, the distance r, that the point is from the origin. If we take a look at the angle theta, which is again the argument of the complex number, we'll know that the cos of theta, cosine of theta, is x over r because it's adjacent over hypotenuse. So we can say that the distance x, which remember is the real component of the complex number, is equal to r cos theta, just by moving this r across here. Now, if we look at sine theta, which is opposite over hypotenuse, that is equal to y over r. And thus we can define y as r sine theta, similarly by moving r across. So we know that the real component of the complex number can be given by r cosine of theta, and the imaginary component can be given by r sine of theta. If we combine these two to give you z, the complex number, an arbitrary complex number, r cos theta plus I r sine theta. That will be z now, because remember, this distance represents the imaginary component, so we have to have that I here. We can factorize out the r, and we are left with z is equal to r into cosine of theta plus I sine of theta. That is what is known as the polar form of the complex number. Thus, for any complex number, z is equal to x plus iy. That same complex number can be represented by r into cosine of theta plus I sine of theta. Let's do that with this point that we have here. So this point is 4 plus 4i. I'm going to bring back the triangle to help you visualize this. Right, so the distance r we can find out using Pythagoras' theorem. R is going to be the root of this side squared plus this side squared, which is y squared plus x squared, or in this case, 4 squared plus 4 squared, which is the root of 32, which is the root of 16 by the root of 2, which is 4 root 2. Theta, we can use tan to figure out, because we know this distance, the opposite, and we know adjacent. If you know the opposite of an angle and the adjacent of an angle, you can figure out the angle using tan, because tan theta is opposite over adjacent. So theta will be the tan inverse of 4 divided by 4, which is pi over 4 radians, or 45 degrees. So this number, 4 plus 4i, can be represented by 4 root 2 into, just like before, cosine of theta plus I sine of theta. In this case, cosine of pi on 4 by I sine pi on 4. Okay, just briefly, I'm going to bring in a formula that you do not need to know, rather, how it comes about, but it just says that cosine of theta plus I sine of theta is equal to e to the I theta. The proof for this is very complex, so we're not required to know it as students. And thus, z, the complex number, can also be written as r e to the I theta. All you do is you say that because this equals this, you just make the substitution. So you replace cosine of theta plus I sine of theta with e to the I theta. What this does is it brings about some new interesting facts about a complex number in the complex plane. Now, because, let's suppose that we're going to multiply two complex numbers. Any complex number, z1 multiplied by z2. If we rewrite them in polar form, we say that z1 will be r1 e to the I theta 1, and z2 will be r2 e to the I theta 2. They combine to give you another arbitrary complex number, z3, and we know that, well, these will multiply by each other. And that gives us the first rule, which is that when you multiply two complex numbers, the modulus, or magnitude, the distance of the point from the origin, is the multiple of the two magnitudes of the complex numbers. And because of the laws of logs, or laws of indices, I should say, when you have the same base, you add the exponents when you multiply. Remember, we can pull it in here. A to the m by a to the n is a to the m plus n. Thus, when you multiply e to the I theta 1 by e to the I theta 2, you combine the two angles and the final product will have an angle of the addition. If you were dividing z1 by z2, let's say you were dividing, instead this would be r1 divided by r2, and this would be theta 1 minus theta 2. Let's use that and try and figure out what would happen when we multiply these two complex numbers. So we have z1 as 2e to the I pi over 2, and z2 as 3e to the I 3 pi over 4. One small problem exists though. When we add these two angles, we get an argument that is outside of the range that we originally said we could have. Because pi over 2 plus 3 pi over 4 is 5 pi over 4, which is bigger than pi. So if we think about where that would be on the complex plane, well, if this is pi, and we're increasing by going this way, 5 pi over 4 would be somewhere around here. So let's suppose we have that point here, somewhere around here. Well, the argument is not going to be 5 pi over 4. What we do is we adjust the argument so that it fits within the range. So remember, whenever you have a complex number in either of these two quadrants, it's negative and you go this way. So all you have to do now is pretend that the complex number is here, and you find out the argument by going from the real axis across. And because this is 5 pi, this whole thing here is 5 pi over 4, you can subtract the entire thing from 2 pi, or you can also say that this angle here will be pi over 4, and you get this argument, minus 3 pi over 4, because this is pi over 2, and this is minus 3 pi over 4. So the final number you'll end up with is z3 is equal to 6e to the I minus 3 pi over 4. Okay, that will be it for this video. The second half of complex numbers will be out soon. Thank you very much for watching.